Morning. Am I audible to you guys?
Yes, ma'am.
Okay. So in last class, we mainly discussed about first order logic, which is another type of logical representation of knowledge base. So a few points to remember in case of first order logic is that it is more like our natural language. It has a bit more expressive power than your propositional logic. Then we can design or means design statements like that allows all, some, that type of relationship. It also allows to design words like son of, brother of, those kind of relationships. And there are two important things are universal quantifiers and existential quantifiers. So universal is when we use like all or everyone, everybody like this. And existential means some, at least one, those type of relationships. Okay. Then we also saw some examples how we can create first order logic from a statement and on. So next is the inference rules for first order logic. Just like we had inference rule in case of propositional logic, here also there will be some inference rule. But before going to the inference rule, one small thing need to know. The term is knowledge engineering. Okay, let me share my screen first. Knowledge engineering. So what is knowledge engineering? Knowledge engineering is just the process of constructing your knowledge base. Constructing a knowledge base in first order logic. First order logic. Okay, so knowledge engineering means constructing a knowledge base in first order logic. Okay, so in knowledge engineer there will be a knowledge engineer. Knowledge engineering is the process and there will be a knowledge engineer. He will investigate a particular domain, will learn important concepts of the domain, and will generate a formal representation of the objects and the relationships. Okay, that's the main function of the knowledge engineer. So he will basically construct this knowledge uh, base based on a particular domain with the related knowledge, then it will formalize the objects and the relationship. So this is the main flow diagram for knowledge engineering. So what happens here? The first step is identify the task. Okay, identify the task means a knowledge engineer should be able to identify the task by asking a few questions like, do the knowledge base will support, what kind of facts will be available for its specific problem. So the task will identify the knowledge requirement needed to connect the problem instance with the answers. Okay. Next will be the assemble of relevant knowledge. That means what? It should be like knowledge engineer should be like an expert in that domain. Right. Engineer is the expert in a particular domain. So if this is not the case, means if he is not expert in that domain, then he should work with the real expert to construct their knowledge. Okay, and that concept is known as also knowledge acquisition. Okay, this part you can also say knowledge acquisition. See, it's an engineer, he will basically construct this knowledge base based on a particular domain. But if he doesn't, he should be the expert. If he is not the expert, then he will just take help of the other expert to create the knowledge base. Okay. Then comes decide on a vocabulary of constants, predicates, and functions. Vocabulary means you basically will decide what predicates, functions, constants should be used. Constants, functions should be used. Okay, so translating important domain level concept into the logical level concept. Okay, so here the knowledge engineer asks questions like, what are the elements which should be represented as objects? Okay, then what function should be chosen? Okay, after satisfying all the choices, the vocabulary is decided. Okay, like it is known as also ontology department. Suppose he is working in ontology department, then ontology determines the type of the thing that exists but does not determine their specific properties and the interrelationship. Okay, then comes your encode general knowledge about the domain. So it's just like our normal engineering process. Even if you do any project, first you need to identify the task, then you have to gather the relevant information which will be required to build a project. Then you have to decide the vocabulary. Here it is predicates, constants, function, etc. But in normal case, it will be like what are the main important terms? What should be the function? What should be the entities and all? Then encode general knowledge of the domain. Then in this step, what it will do, the engineer will pen down the axioms for all the chosen vocabulary terms. Okay, so here there might be some misconception between the vocabulary terms. Say encode description of the specific problem instance. Encoding general knowledge of domain means first it will just encode description of the specific problem instance. Okay, like we write the simple atomic sentence for the selected vocabulary term, then we encode the chosen problem instance. Okay, then can be like raise queries to the inference procedure and get answers. So it is like a testing step. Okay, so we apply the inference procedure on those axioms and problem specific facts which we want to know. First, we will simply select some of the problems uh, some of the known knowledge. Then we will create the axioms from the selected vocabulary. Okay. Then we will just encode the that description of the specific problem instance. Okay. And then we will raise the queries to to the inference procedure, and we will try to get some answers. Okay. And finally we will just debug our knowledge base, or we'll try to find out whether there are some errors or not. It's just like your normal software engineering life cycle. Identify tasks, assemble relevant knowledge, decide the vocabulary, encode your general knowledge, then encode description of problem, then post queries like what questions should be asked, like it's more like testing step. Okay, then you need to debug it. Okay, so that's about your knowledge engineering. Now the main part is the inference in your first order logic. So just like in propositional logic, inference in FOL logic also deduce new facts. Same process, it just deduce new facts or sentences from existing sentences. Okay, so before jumping into the inference, you have to know certain terminologies, and those terms will be used in your inference. First is substitution. So it is like a fundamental operation performed on your terms and formulas. So substitution is like the complex representation of your quantifiers. Okay, so if you write, just directly give example like suppose f a x. Okay, so this will mean we can substitute constant a in place of variable x. Okay, means substitute a constant a in place of variable x. Okay, it's just like our normal substitution. Basically used for terms and formulas. Sometimes we can just substitute some of the variable with another constant. So we can write it like this: a by x. That means you are going to substitute a in place of x. Okay, then second is equality. So in first order logic, predicate and terms are not the only way to generate your atomic sentences. Okay, we can use equality too. Okay, equality symbols will specify that the two terms refer to the same object, just like the normal literal meaning of equality. It will just tell you that it's referring to the same object. So example, you can say like brother John is equal to Smith. Okay, so both are same. Brother John is equivalent to Smith. Okay, so this is the equality. Another example you can say like negation of x equal to y, which is equivalent to your x not equal to y. Correct? X equal to y, then you give bracket negation, which is just equivalent to x not equal to y. So in both ways, it is valid. You can either represent equality like this, both brother John and Smith referring to the same thing, and also like xy negation is x not equal to y. Okay, so these are the two main things, two main terms, equality and substitution. Just wait. Sorry. Now comes the inference rule. These two things will be used when we will use the inference rule. There are four inference rules in first order logic. Okay, first is your universal generalization. Universal generalization. It states that if, okay, just writing, if premise PC is true. Remember, in case of first propositional logic, we had inference rule like modus ponens, modus tollens, syllogism, and all. Here again, four things. First is the universal generalization. So it means if premise PC is true for any arbitrary element C in the universe of discourse, then we can conclude as for all x p of x. Okay, So this thing can be represented as, if PC, then for all x, P of x. So this rule can be used if we want to show that every element has similar property. This means every element has similar property in basic terms. Okay. Example can be like, suppose PC means a byte contains 8 bits. Okay. So your PC given is a byte contains 8 bits. So for all x, Px, you can say all bytes contains 8 bits. It will be true. If this one is true, then this one is true too. Universal generalization. So it's mainly used for to show that every element has similar property. So in the universe, if one thing has a particular property, then we can say all of such things has the similar property. Like here, PC, a constant term, is a byte contains 8 bits, right? So we can just conclude that all bytes contains 8 bits, correct? Got it? It's like an orange is orange in color. That means we can just say that, conclude that all oranges are orange in color, something like this. If one thing is true, then we can just say all of that thing will be true for that particular statement. Okay. So this is generalization. Next comes your universal instantiation. Universal instantiation. So this thing, this instantiation rule can be applied multiple times to add new sentence. Okay, can be applied multiple times to add new sentence. Okay, so here your new knowledge base will be logically equivalent to your old knowledge base or previous knowledge base. So using this one, you can add multiple lines, but whatever new line or new sentences use, they both new knowledge base and the previous knowledge base or old knowledge base will be logically equivalent. So here mainly we can infer any sentence obtained by substituting a ground term for the variable. Okay, it's like this. That means, this means that if any sentence PC by substituting a ground term C, this is C is like a constant. Okay, this is like a constant within domain X. C is your constant within the domain X from, for all X, P of X for any object in the universe. So basically, universal instantiation is like opposite of your generalization. You can represent it as for all x p of x, then PC will be true. So normal example can be like every person likes ice cream, likes ice cream, which is, we can say, for all x p of x, then we can infer that John also liked ice cream, which is your PC. Okay, this is instantiation. It's just opposite of generalization. So if I say every person likes ice cream, then I can just say John, Ram, any names. I can take any names likes ice cream. Okay. Just remember the main natural language like lines. Then another example here can be all kings who are greedy are evil. So this line we can represent with the help of FOL like for all kings and those are also greedy. That means both king and greedy, x is the variable here, implies evil. Okay. So this is the FOL of this particular line. All kings who are greedy are evil. We can write for all kings as greedy equal to your evil. So from this line, we can infer other things like King John greedy John equal to your evil John. X is variable, right? We don't know what it can be. So I can just instantiate that I'm just talking about one person, one John. You can also take other king, King Arthur, greedy is your Arthur, so he just evil Arthur. Then you can also instantiate like King Father John, and greedy father of John, is your evil John. Okay. So this is universal instantiation. Previous one was generalization. Just remember, in generalization for all x, px means pc. This is your instantiation. And in case of generalization, if pc, then for all x, px. It's like if a byte contains 8 bits, then all bytes contain 8 bits. If one king is evil, then you name anyone, everyone will be evil. Okay. So third one is your existential instantiation. Okay, this one is also known as existential elimination. So this can be applied only once. The previous instantiation universal you can use many times, multiple times. Here you can apply just once to replace existential term. Let's say sentence. And here your new KB is not logically equivalent to your old one. Old knowledge base. Okay. So here you infer PC from existential of X and Px for a new constant C. So you can write this one like this, okay? If existential quantifier Px for some Px, then Pc is true. Okay. So just that the restriction is that the C used in the rule must be a new term for which PC is true. PC should be a new term here. Just write restriction. Restriction is that used in the rule must be a new term for which PC is true. Okay, so example you can say given term for X crown X on head X and suppose John. Okay, so here we can infer that crown K N on head P John, as long as your K does not appear in your knowledge base. So here K is the constant symbol. And this is called column constant. Column constant. SKOLEM. So your existential instantiation is the special case of columnization process. So it's not that complicated, just that if it's mainly used for your existential quantifier, variable is there, crown X on head and on head X John, then you can just replace this X with another constant K. Okay. The fourth one is the existential introduction. Okay, this meeting is going to end. Introduction. Okay, so this is also known as your existential generalization. So since it's a generalization, this is just opposite of this one. Okay, just the opposite of this one means you can represent it as PC for x e of x. Okay, it is like if there is some element C in the universe of this force which has the property P, then we can infer that there exists something in the universe which has the property P. For example, like Jane got good marks in English. That means we can infer that someone got good marks in. It is like sometimes we just say, right, we do the name of a person, but we don't tell the name. Instead, we just say someone got good marks, someone is intelligent, something like that. Okay. If main sentence is that John got good marks in English or Jane got, no matter who got good marks in English, we can infer that someone got good marks in English. Okay. If at least one person is getting good, there is a variable or constant, then we can just generalize it like this way, someone got these things. Okay, these four inference thing. Universal generalization, just remember two universals and two existential, and in both cases one is generalization, one is instantiation, and the last part is introduction, but still is just the generalization. So whatever will be the generalization, instantiation will be the opposite one. Okay, just remember that tricks. It's just opposite of each other. Universal and universal instantiation, same existential instantiation and existential generalization. That's it. Okay, that's all for today. Stop sharing. I might be going a bit faster because I also want to finish the syllabus. I'll provide you the notes in this weekend, okay? So kindly switch on your cameras for a while.